Welcome to the Explainer. In the digital world, how you organize your information is, well, it's everything. If you get it right, your app is just lightning fast. But if you get it wrong, the whole thing can grind to a halt. So today, we're going to demystify a really foundational concept, the linked list. And we're going to see why, sometimes, a flexible chain is way more powerful than a rigid block.
Okay, so let's dive right in by starting with something we're all probably familiar with, an array. Just think of it like a tightly packed box, like an egg carton, where every single item has its own specific numbered slot.
And this structure is fantastic for one thing in particular, speed. Because all the elements are stored neatly right next to each other, your computer can do a super quick calculation and just jump directly to any item instantly. We call this O of 1, or constant time access, which is really just a fancy way of saying it takes the same tiny amount of time whether the array has 10 items or 10 million. It's incredibly efficient.
But here's the catch. What happens when you need to add something new smack dab in the middle? This is where that beautifully organized box creates a major headache. And suddenly the array's greatest strength, its rigid structure, becomes its biggest weakness.
See, to make room, you have to perform a really costly operation. First, you find your spot, and then you have to physically shift every single element after it one position over. Now, if your array has 1 million items, that's 1 million moves you have to make just to insert one new piece of data. It is slow and it is super inefficient.
So what's the alternative? Well, instead of that rigid box, what if our data was stored more like individual links in a chain? Imagine each link is its own separate piece, but it holds a crucial secret, the location of the next link it's connected to.
And that right there is the core idea of a linked list. Each piece of data, which we call a node, can be scattered literally anywhere in your computer's memory. It doesn't matter where they are, because each node contains a pointer, which is basically an address that tells you exactly where to find the next node in the sequence.
So the crucial point is this fundamental difference. An array is one single solid block of memory. A linked list, on the other hand, is a flexible, dynamic chain of individual links, and it's this flexibility that really gives it its power.
Now let's see how this basic chain concept evolves to solve even more complex problems. Because it turns out there isn't just one type of chain. There are actually several really powerful variations.
So the simplest form is the singly linked list. Each node is really straightforward. It holds your data, and it has one pointer that points to the next node in the chain. And the very last node? It just points to null, which is kind of like a sign that says, hey, the chain ends here.
But with a singly linked list, you can only move forward. So what if you're at a node in the middle of the chain and you suddenly need to know what came before it? Well, you'd have to go all the way back to the beginning and walk the whole list again. Not very efficient, right?
The doubly linked list solves this beautifully. It upgrades the node by adding a second pointer, a previous pointer. So now each link knows not only what's next, but also what came before. It creates this perfect two-way street for traversal. You can move forwards and backwards with total ease.
And the impact of that one extra pointer is huge, especially when it comes to deleting a node. With a doubly linked list, you can remove an element instantly. We're talking O of 1 time. Why? Because the nodes on either side already know how to find each other. You just tell them to point to one another and you effectively snip the middle node right out of the chain. That's a massive performance gain, even though it does come at the cost of a little more memory.
Okay, so let's take this chain concept one step further. What if we just got rid of the end altogether? What if we created a list that just loops back on itself? And that's what a circular linked list is. The last node doesn't point to null, it points right back to the very first node, creating a closed loop. This is perfect for continuous processes, like a music player's playlist on repeat, or a server handling requests in a round-robin fashion.
So we know linked lists are great for adding and removing items, but they're pretty slow for searching since you have to check every single node. But what if we could give our linked list a turbo boost? Is it possible to make it as fast to search as something more complex, like a balanced tree? Well, the answer is yes.
So just imagine our base layer is a standard sorted linked list. To find a specific item, you've got to take the slow, scenic route, visiting every single node along the way until you find what you're looking for.
Okay, now let's build an express lane right on top of it. This is another linked list, but it only connects to, say, every other node in the base list. So now you can travel along this express lane to quickly jump halfway down the list, and then just drop down to the scenic route to find your exact destination.
But why stop there? We can add even more layers, creating these super highways that let us make even bigger jumps.
You start on the highest, fastest layer, you jump as far as you can, and then you drop down layer by layer until you're on the main road right next to your target. And this is the power of a skip list. It uses these multiple layers to get incredible search speeds. We call it a probabilistic structure because which nodes get to be in the express lanes is determined randomly, but it just works out beautifully. It achieves O log n search time, which basically means every time you double the size of the list, it only takes one extra step to find something. It's a really clever trade-off. Use a little more memory for these express lanes, and in return, you get blazing fast performance.
So, with all of these options, how in the world do you choose? I mean, no single data structure is perfect for every single job. It really is all about understanding the practical trade-offs between the block and the chain.
And this slide right here brings us to the key takeaway of this whole discussion. The choice is a trade-off. If you need to jump to elements by their index instantly and your data doesn't change a whole lot, an array is absolutely your best friend. But if your application involves constant insertions and deletions, a linked list is the clear winner, saving you from all of that costly shifting.
Oh, and don't forget about the memory cost, because that flexibility isn't free. On a 64-bit system, a simple integer that takes up 4 bytes in an array, well, it suddenly needs 12 bytes in a singly linked list to account for that pointer. And in a doubly linked list, it jumps all the way to 20 bytes. That memory overhead can really add up, especially in large-scale applications.
So how can you truly master this concept and actually start applying it effectively? Well, like any skill, it's all about starting with the basics and building your way up.
You know, the best way to learn is by doing. So here's a path you can follow. Start by building your own simple, singly linked list from the ground up. Once that clicks, you can tackle classic problems like detecting a loop in a list. And then when you're ready, you can challenge yourself with advanced applications, like designing an LRU cache, which cleverly uses a doubly linked list to manage memory.
Ultimately, it all comes down to this one question. Now that you understand the fundamental trade-offs between the rigid, fast access block of an array and the flexible, dynamic chain of a linked list, the real challenge for you is knowing exactly which tool to choose for your next project, because your answer is what will define its performance.